Good morning, everyone. Can you hear me okay? Okay. I'd like, first of all, to thank you all for attending this event this morning. Let me start by saying just a few words about myself. My name is Amy Maybach, and I'm an environmental scientist with the United States government. I have devoted my career of 18 years with the United States government protecting our nation's valuable water resources. I'm here today to present on the United States Clean Water Law. The United States has vast water pollution problems. Not that long ago, I remember in parts of the United States where untreated sewage would discharge into the ocean after every major rain event. The pollution was so severe, people couldn't go into the water until days after the rain stopped. So today, I'm going to discuss both the challenges and some of the solutions to the United States water pollution issues through the enactment of a clean water law. And also discuss how the United States is addressing water insecurity and scarcity today. This presentation is designed to act as a starting point for questions. So please feel free to ask me any questions along the way. And lastly, a quick disclaimer. The United States Clean Water Law is very comprehensive. And due to time constraints, I won't be covering every section of the law here today. So let's get started with some background. Next slide, please. In the United States, early water laws were in place to protect boat navigation and did not prohibit water pollution. Since there were no laws to protect water quality, the United States had significant amounts of untreated sewage, industrial waste, and agricultural runoff entering our nation's waters. In the late 1940s, the United States Congress passed a water pollution control law. However, this law failed to provide money for the construction of sewage treatment plants, restrict industrial pollution, or agriculture runoff. So water quality improvements were minimal at best. Next slide. Since this 1940 law was ineffective at controlling pollution, many rivers continued to be severely polluted and would even occasionally catch on fire. The picture here shows one such river which routinely caught on fire and was considered normal to be on fire. I'd like to draw your attention to the sign in the upper left that was along the river shoreline. It shows that the river was flammable. And as we know, water should never be flammable. This sign demonstrates how much pollution the river contained. Next slide. Although United States Congress made some attempts in the 1950s and 1960s to strengthen the Federal Water Pollution Control Act, water pollution problems continued to increase. And by 1970s, virtually every river and lake was in a crisis condition because of uncontrolled dumping of waste. This pollution was so severe, the river described in the last slide and shown here again in the fire on this slide was described as a place where a perfect person does not drown, but decays. Next slide, please. By 1969, one of the many river fires drew national media attention when it was published in Time magazine. The media attention resulted in widespread environmental concern. Prompted by this national concern, the United States Congress took notice. And in 1972, the previous ineffective water pollution control law from the 1940s was significantly amended and became known officially as the Clean Water Law. The Clean Water Law created a shared balance for clean water between the federal government and our 50 states. Next slide, please. Next, I'll discuss a brief overview of the 1972 Clean Water Law. Next slide, please. The 1972 Clean Water Law is the primary federal law governing surface water pollution. As you can see from the slide, the goals of the Clean Water Law were very ambitious. The United States did meet some of the goals by the 1980s. However, still today, not all waters are fit for fishing or swimming, so there is still plenty of work to be done. And to provide some context, the Clean Water Law does not set standards for drinking water, but rather the sources of drinking water, such as rivers, lakes, and even the ocean. In the United States, standards for determining if water is treated enough to be potable is regulated under a different law. This separate law also regulates groundwater, which is a major source of drinking water in the United States. Next slide, please. The Clean Water Law establishes the basic structure for regulating pollutants or contamination entering our nation's water and the acceptable level of pollution designated for those waters. The law really tries to prevent, reduce, and ultimately eliminate pollution in our nation's waters. Next slide, please. First, before addressing the major components of the Clean Water Law, I want to address the exclusions. In general, agriculture is exempt from the Clean Water Law. This exemption includes agriculture, rainwater runoff, and return flows from irrigated agriculture. Instead of regulating agriculture runoff through laws like the Clean Water Law, the United States manages this water through the use of best management practices, which I'll discuss further. Next slide, please. These are just some examples of the best management practices used in agriculture. Things include leaving crop residue on the soil surface to reduce water runoff and soil erosion. Having small areas or strips of vegetated land designated to slow water runoff and capture pollution. In managing all nutrients and their inputs to help ensure the nutrients are available to meet crop needs while reducing nutrient runoff. Next slide, please. So going back to the Clean Water Law, a major part of this law is to set water quality standards for surface waters. Water quality standards are developed to protect the uses of the water, for example, fishing, or maybe water that will be used as drinking water after it's treated. To protect these uses and achieve the desired water quality, we set a standard that limits the amount of pollution allowed in the water. Water quality standards really look holistically at the whole watershed. And water quality standards can help identify waters that need restoration and set goals for achieving the necessary improvements. Next slide, please. Also, the Clean Water Law helps municipalities or cities obtain low-cost funding through a loan program for water and sewage treatment plants, as well as non-point source pollution controls like the agricultural best management practices discussed previously. However, industry must pay for the treatment of their own waste and cannot use this loan program, as the United States operates on a pay to pollute approach for industry. Next slide, please. Let me go back to the story I told you earlier. Remember the river shown at the beginning of this presentation? I wanted to show the stark difference of this river exactly 70 years apart. This river was once a symbol of calamity, but from it came an environmental movement to needed change. The Clean Water Law was instrumental at reducing pollution in this river, as well as all of our nation's waters. Significant water quality improvements have been made due to limiting pollution. However, we still have work to do. Next slide, please. New challenges are arising in the US due to water scarcity. Drought has become common in much of the United States. And although not specifically part of the Clean Water Law, water resource management due to water insecurity has become a focal point in the United States. A little background on why this is. The United States population has doubled over the past 50 years. And at least 80% of the country anticipates water shortages by 2024, as well as climate change impacts. One example of water resource management shown here in this slide is rainwater harvesting, which provides both environmental and economic benefits. By using rainwater for uses in toilets, bathing, and irrigation, you reduce the demand for potable water and conserve water resources. These photos show rainwater being captured in tanks and barrels from the roofs of businesses and a residential home. Next slide, please. Next, I'll discuss some case studies which highlight how the Clean Water Law is implemented and how agriculture is managed without being subject to the Clean Water Law. In the case shown on this slide, the United States caught a disposal company illegally dumping raw sewage. This company did this activity for 10 years. And they would do it in the early morning hours to avoid detection. As you can see from the slide photo, the pump is in the yellow circle and was photographed at night when the dumping occurred. This company was brought to the attention of the United States by a citizen complaint, even though the company did this activity at night. Using the authority of the Clean Water Law, the United States was able to enforce against this company and send the owner to prison and levied a major fine for this criminal activity. This is an example of how we implement the Clean Water Law in the real world. Next slide, please. As discussed earlier, agriculture is exempt from the Clean Water Law, but is instead managed through best management practices. I want to show an example in the next 2 slides of how we still achieve water quality results without being subject to the Clean Water Law. In this case study, a pesticide called chlordane and sediment were contaminating the nearby surface water called Pigeon Creek. This creek was used for fishing and as a source for drinking water. Crops in this area were routinely treated with chlordane until the 1980s, when this chemical was banned by the United States. However, high levels of chlordane remained in the crop soil. To address this issue, an agricultural community installed 50 best management practices to reduce soil erosion and chlordane levels in Pigeon Creek. These best management practices included filter strips, grass waterways, field
I am so sorry, everyone. My internet completely crashed. I am resharing the screen now.
Thank you. If you could advance 1 slide, that would be great. There we go. Perfect, thank you. Another case study shown here is related to diazinon, also a pesticide used to control insects. Widespread use of diazinon resulted in toxic levels of this pesticide in a river called Butte Slough. Exposure to even low concentrations of this pesticide, 1 microgram or less, can cause genetic damage in fish and reproductive losses. The levels in this river were also so high, they exceeded the water quality standard for diazinon. Therefore, an agricultural implementation group composed of commodity boards, pesticide registrants, and farm organizations implemented a diazinon reduction strategy. This included farmers installing best management practices, such as replacing flood irrigation with sprinkler systems, installing filter strips, planting cover crops, and limiting diazinon use. Water samples taken from the river before the diazinon reduction strategy routinely exceeded the water quality standard. However, all water samples taken after implementation of this strategy have complied with the diazinon water quality standard. So as demonstrated, best management practices can be used to control and improve the quality of agriculture runoff to surface waters. Next slide, please. In closing, the Clean Water Law was prompted by national concern for our nation's water quality. The implementation of low-cost funding was instrumental and allowed for the construction and upkeep of both water and sewage treatment plants. Even though agriculture is exempt from this law, agriculture runoff can be controlled through the use of best management practices. Lastly, clean water and economic growth do not have to be incongruent goals. And in fact, clean water promotes economic prosperity. As we continue to learn, we need clean, safe, and ample water supplies for economic development. Thank you so much for your time today. I look forward to any questions you may have. Next slide.
Amy, thank you so much for that presentation. I would like to ask our colleagues on the line who are participating, if they have questions now, they can type them in the chat box. During the presentation, we already had a request for a copy of this presentation, and I can assure all of you that we are going to add links so that you'll be able to download this presentation in Russian, in Uzbek, in English. You'll be able to get a copy in the language that's easiest for you to understand. Somewhat later, we will add that, or Elizabeth, you can assist us with that. So to be sure, if you'd like to have a copy, you can also add an email into the chat box, and I will make sure we send it to you. And if nobody has any questions just now, what we can do is, if you do have questions a little bit later, you can type them in the chat box, or you can bring them up, and we will move on to our next presenter. That's Neil Dubrovsky, and he can entertain questions as well at a later date. Oh, I see Elizabeth has just put the link for the presentation. So Neil, if you'd like to get ready, that would be helpful.
Ready to proceed, Elizabeth?
I think so. Hopefully everyone can see the screen with Neil's presentation.
Okay. Well, thank you very much. I'm honored to be able to share some of my experience with you today, and thank you for attending our lectures. A little bit about my background. I have a PhD in hydrogeology from the University of Waterloo, Canada. And I spent 34 years working for the US government for the United States Geological Survey. The USGS is part of the Department of Interior. And I spent most of this time studying water quality. And much of that was in directing teams studying the water quality of the nation. And that's what I will share with you today. Next slide, please, Elizabeth. So this is a broad outline of what I will speak about. I'll address why evaluate groundwater quality. What are the broad goals of a national scale groundwater quality assessment? And then describe approaches to assessing groundwater quality. And I'll share examples from the United States groundwater quality assessments. Next slide. So why evaluate groundwater quality? Well, we evaluate groundwater quality to effectively develop policy, develop regulatory structures, and to manage groundwater resources. And especially in a semi-arid and arid area, groundwater resources touch everything. The quality of groundwater limits its use for drinking water, agriculture, industrial development, or it imposes a cost if the water quality is unsuitable for one of these uses. Next slide. For the United States, there had been lots of work on the quantity of water in the country, rivers, streams, and groundwater, but not water quality. So in the late 1980s, the US Congress asked the US Geological Survey, what is the status of the nation's water quality? And is it getting better or worse? And I'll probably mention this again, but regulatory programs that target one sector are biased. They usually sample just part of the water resource and can't answer very broad assessment questions. Next slide, please. So, what are the broad goals of a national scale groundwater quality assessment? So I've listed 3 here and snuck a 4th one in at the end. The first is the status. The assessment should identify the current water quality impairment and describe the spatial patterns of occurrence and concentration of chemicals of concern. Second is trends. It should answer the question, how is the quality of groundwater changing over time? Is it getting better or worse? And the third component is it should tell us, we should understand, we should find what are the major natural and human factors that influence groundwater quality. Now, this part that we call understanding, when we put the understanding together with the characterization of the distribution in space, we're able to develop statistical models that do the last thing, which is forecast. So we can project and understand what the quality is in places we have not sampled, and also project what will happen in the future. Next slide, please. Okay, so now I'll talk about my experience with the assessment that we did in the United States. And I'll talk about somewhat about the evolution of our studies, how our approach changed. Next slide, please. So first, I want to distinguish a small point, but important. Many people think that assessment means monitoring. But monitoring is data collection. Assessment is evaluating the data to improve our understanding of the status. Next slide, please. So this is something that our study was not. In the United States, there was a lot of focus on groundwater contamination from industry, from what we call point sources, such as tanks or industrial accidents. There's a lot of attention because these were in urban areas with lots of population. But for the most part, these are of very limited aerial extent and only impact a small portion of the water resource. Next slide, please. Instead, what we focused on were what we call non-point sources. So we were assessing non-point source pollution. This is diffuse contamination sources from urban development, from agricultural activity, or from natural sources. The graph on the right shows one example of a very typical non-point source pollution problem. Nitrogen is an element that's critical for life. But too much nitrogen in surface waters or in drinking water leads to ecological or human health problems. The slide on the right in red shows the increase in the use of nitrogen fertilizer from 1 to over 12 million tons in the since 1945. In the same period, the population of the country more than doubled, which is also puts nitrogen in the environment through sewage release. So within the past 5 decades, there's been a huge increase in nitrogen across water in the landscape. Very, very typical non-point source problem. Next slide, please. So a comment about the evolution of the assessments. What it is, it's large scale, but it's based on aquifers. There should be. But the program, as originally designed, is shown on the left-hand side. And what we see in green are watersheds. So the areas that we studied were defined by watershed boundaries. But the properties of the rocks that control groundwater contamination are defined by the aquifers they're in. And the aquifers, the principal aquifers of the United States are shown on the right. So for 20 years, we were following an approach that, as you can see in many cases, these green areas intersected several aquifers, but only parts of them. So we had, as a result, an incomplete characterization of the quality of the water in these aquifers. In 2010, we finally changed the design so that our sampling approach was based on the slide on the right, that is, the distribution of the aquifers. Again, because the properties of the aquifers control the chemistry. Next slide, please. I'm not going to talk about this much, but the important point is what is needed is an approach that provides an unbiased picture of water quality. And as I noted, for example, a regulatory program will be targeted at places there are problems. The data from that will be biased to capturing a lot of those problems. We needed the picture of water quality across the entire resource. So we adopted a grid-based design, and skipping the math, the result is that we could report the results with a high degree of confidence that was very rigorous, and usually sampling 60 data points in an area would identify a target of contamination of 1% of less of that resource. Next slide, please. The other thing that's important in these assessments and the way we design them is we had components that addressed a large number of scales, and it integrated water quality information at a wide range of spatial scales. So again, we see the map on the right that shows the 25, what we call principal aquifers that we studied. They accounted for almost 90% of all the water use in the nation. And many of them were on the order of 1,000 square kilometers, some much larger. One click, please, Elizabeth. At the next scale, in that red circle, is one principal aquifer, the Central Valley of California. And I'll use examples from this a little later as well. It's a semi-arid, surrounded by high mountains with snowpack, not unlike Uzbekistan. And when we go down to the regional area in the San Joaquin Valley, we then could ask questions that were more specific. What kind of contamination do we get from a specific land use? In this case, we studied almond orchards, vineyards, and vegetable crops. And then we could compare the amount of contamination from agricultural chemicals in 3 different land uses. One more click, Elizabeth. Because there was a specific problem with the use of a fumigant in vineyards, we then studied a very small scale, 2 kilometers, in great detail to look at how this pesticide moved through the groundwater. And at that small scale, what we could gain is the understanding of the processes that control the chemical movement. Next slide, please. So what we're doing is we collect very consistent data. I'll come back to that point, which allows us to integrate the water quality information at a wide range of spatial scales. Then patterns that we see in the water quality can be explained by the understanding that we gained at that local scale. And the result is that the data and understanding we gain benefits water management at the local scale, at the regional scale, in all of arid California, and by comparison with other areas through the whole country. But going back to the word consistent, in order to do this and to have data that we can compare in different parts of the country, you must be extremely consistent. Consistent with your design, consistent with your sampling methods, consistent with your laboratory methods. And if you do that, all the data can be used for the whole country or to answer questions very locally. The other thing I'll mention is we're very comprehensive. It's expensive just to get samples. So when we collect samples, this last study we analyzed for over 500 chemicals in the sample. Pesticides, nutrients, industrial chemicals, and so on. Next slide, please. Okay, so now I'll share some of our findings, starting at the largest scale, the nation. This is a similar map of the 25 principal aquifers, and it's showing the 1,458 wells that we sampled. And just to digress for a moment, the country is very diverse. So we have aquifers that are limestone in Florida, are granite in the Northeast, are volcanic basalts in the Northwest, and are sedimentary rocks that are very young in the glacial areas, and some aquifers with water that are thousands of years old. Next slide, please. So here's the broadest finding, and it was a surprise to many people. We found that the natural chemicals, geogenic elements like uranium or arsenic, may affect more people than man-made chemicals. And I say that's a surprise, again, because industrial accidents in cities receive a lot of media attention, in part because there's something we can control, whereas the natural contamination is difficult. The graph shows the estimate of the population that might be affected by geogenic, natural contamination, and it's over 30 million. In contrast, the anthropogenic, the man-made compounds, occur in moderate and high concentrations of concern that might affect only about 7 million people. So a counterintuitive result. Next slide, please. And getting more specific, this slide shows a subset of the earlier wells. These wells were sampled over 20 to 30 years to identify the change over time in the concentrations. And in this case, the map shows uranium. And the red dots are concentrations above our drinking water standard. And it's pretty clear that uranium is highest in the arid or semi-arid climates in the Western United States. And one can see dots in California and some in Arizona, New Mexico, Colorado. In contrast, in the humid eastern portion of the country, all blue dots, except for a few in Florida, low concentrations in the humid climate. We also found that where concentrations were high, they were also increasing. Next slide, please. So, to examine that, let's back up one slide, please, Elizabeth. Sorry. I just wanted to point out the pink circle is where we will go next, back to the Central Valley of California. Thank you. So in the Central Valley, what we found was that uranium that is naturally in the soils, because they're from the granites in the mountains nearby, was being mobilized in the groundwater. And what we found is that the irrigated agriculture was changing the chemistry of the groundwater. And what happens is there's very sparse vegetation before irrigation started about 100 to 150 years ago. And with the crops on the surface and the irrigation, it increased the concentration of bicarbonate, dissolved carbon dioxide gas. The bicarbonate then moved down in the groundwater, and the carbonate binds to the uranium. They have opposite charges, and the carbonate binds to the uranium, and it causes it to be released from the sediment and mobilized into the groundwater. So the irrigation at the top was moving down into the aquifer and increasing the uranium concentration in the groundwater. Next slide, please. We then worked with a city in the Central Valley called Modesto. And Modesto had found some high concentrations in their wells and were unclear why. And it became a very interesting story. In the winter, because the demand for water was low, the city turned off some of their wells. So again, we have shallow water from the crops nearby with high uranium. And one click, please, Elizabeth. When they turned the wells off, water would flow down the well. Is that animation running? Click. Ah, that's interesting. So you can see at the bottom, the water would move down the well and accumulate as a bubble in the aquifer at the bottom of the well. Next slide, please. Then in the summertime, in the spring actually, when the water demand went up, they would turn that well on. Let's see if we have any animation. One click, please. And when they turned it on, the water would draw that bubble of high uranium water up the well. Unfortunately, they took their sample in the spring to analyze at the lab to measure their regulatory compliance with drinking water standards. And that first early spring water had the high uranium. So they were violating standards. But as they continued to pump later in the year, the concentrations would decrease because that bubble at the bottom had been pulled back out. So it turned out what they were trying to do to save water, turning the wells off, created the problem. The solution then was simply not to turn the wells off in the winter, these wells that have that problem. Another way would have been to blend water from a well with high uranium with the water from a well with lower uranium. One more slide, please. And the last thing is forecasting. Forecasting is very, very fun, exciting. It's and actually the methods we use do qualify as artificial intelligence. They're complicated statistical models called machine learning. And the way you build them is by these three small maps on the left. These are examples of factors that help explain where a chemical is. How much precipitation, what kind of land use, what kind of soils, and so on. So we collect sometimes hundreds of explanatory variables. And then the model relates the occurrence of the chemical to these variables. And the result is a statistical model that can predict where the chemical is. And we've similarly built models that will predict how the chemical concentration may change in time as it moves through the aquifer. So these are very powerful techniques, and we've been doing this for several years now. The reality is you cannot sample everywhere. So these methods are very powerful. The example on the right is a map of the country showing the concentrations of nitrate. The red areas are areas with concentrations greater than allowed in drinking water. And again, these are forecasted by the statistical model. So that is the story I have for you today. Next slide. And I hope it's a small introduction to the way we have assessed the groundwater resource quality in the United States. And I'd love to hear about issues that you have that we might be able to adapt some of these approaches to benefit your management of your water resources. Be happy to take any questions now. And thank you again for the invitation to speak.
So at this time, we're happy to take questions. I see we have someone with a raised hand. Please go ahead.
Yeah, I am Bakhtiar Karimov from Tashkent Institute of Irrigation and Mechanization Engineers. So you know that, Professor Neil, above all, thank you very much for very interesting presentation. I am very excited with your in-detail investigations on groundwater pollution. Yeah, this is very important, of course, for us also. So you know that in Uzbekistan, we use a lot of water for as a drinking water source, as well as for irrigation. So my question is, you know that Uzbekistan is among the 10 most largest uranium producers in worldwide, yeah? And our uranium sources are situated on high mountain areas, mainly. We have also in low mountain areas in Fergana Valley, but near to Tashkent, we have a lot of sources of uranium, which are now, we don't use them, but they are still the sources of environmental pollution with uranium and other connected chemical pollutants. So as I have seen, your data received mainly for, to say, arid and semi-arid areas, very detailed data, yeah. And what do you think? What is the, to say, relationship between the uranium pollution sources in mountain areas and in plain territories in Central Asia, in Aral Sea Basin? You know that distance from the, for example, mountains near to Tashkent up to lower Amudarya stream, downstream of Amudarya River, more than 1,000 kilometers. Do you think that we have the impact of uranium pollution from these areas up to downstream of Amudarya River? I mean, as a groundwater as well as the surface water quality. Thank you.
So to make sure I understand, the question is, we see relationship between pollution sources in the mountains and in the plains? Transport of the pollution from the mountains. Look, we have, the answer is yes, but it's very specific. There's very little development in the mountains, very sparse population, but there's a long history by our standards. It's very short by Asian standards. A history of gold mining, and that and other mineral extraction. And those kind of pollution problems translate over great distances. In this case, locally, there are arsenic contamination problems, but the biggest problem is the transport of mercury in surface water systems. And then the mercury moves from the mountains where it was used in gold mining down to the valleys and to reservoirs. And in the reservoir sediments, the biology methylates the mercury. It bioaccumulates in fish, and you can't eat the fish. So that's the single largest problem with water quality, problems moving from the mountains to the valley. But that's the only one I'm very familiar with. And it's not a groundwater problem. Generally, the runoff from the mountains is very clean here. Thank you for the question.
Thank you very much.
Do we have more questions? We encourage folks to either unmute and ask the questions directly, or to use the chat if more comfortable. Our excellent interpreters will certainly help anyone who needs assistance in English translation.
While we're waiting, I believe Amy Maybach, our first presenter, actually had some questions that she wanted to ask the Uzbek audience. So Amy, why don't we start by having you ask your question, and let's see what happens with that.
Thank you, Beth. Yeah, I had a question regarding best management practices in agriculture. And I was just wondering what best management practices, if any, were typically used to control agricultural runoff in Uzbekistan.
Do we have anyone who feels they can answer Amy's question about what techniques are used to control runoff and agricultural pollution in Uzbekistan?
How about somebody from Tiame? You guys are working on irrigation. That's your focus area. There's no wrong answers here. We're just curious. We're trying to learn as well from you.
Yeah, I'm sorry. I think we should somehow to clarify a bit the question. Yeah, which runoff you mean? You mean runoff from the agricultural fields or runoff from the irrigation water sources from rivers, river runoff, or collector drainage water runoff, or you mean environmental runoff or environmental flows? Yeah, we say. What do you mean under this question, or if this
Yes,
was
great.
question, or what was?
Great question to clarify. So the rainwater runoff from the fields or irrigated return flow runoff. So what's coming off of the fields, either from rain or from irrigation? Is that water being, are best management practices used to control the pollution and volume of water running off from the fields?
Okay, then as because I am representative of National Research University Tiame, so and I work since long time on water quality issues in Uzbekistan and Central Asia. So regarding the rainwater runoff from agricultural fields, I think there is almost there is no runoff of rainwater during the vegetation season, because we don't have much precipitations during the vegetation season. During the winter and autumn-winter period, yeah, but all of these precipitations runoff are under monitoring of Hydromet Service and Ministry of Water Resources of Uzbekistan. So regarding the runoff from the agricultural fields after the irrigation or after the watering, I would say, yeah, so-called collector drainage waters, they are collected, you know, I don't explain how we collect this, but they are also under control of Ministry of Water Resources. Ministry of Water Resources takes monitoring of collected drainage waters runoff, and also in some degree quality of these collected drainage waters from agriculture. So regarding the natural waters monitoring, this is the issue of Uzbekistan Hydromet Service Center, Center for Hydromet Service. They are conducting very detailed monitoring of surface water's quality, including some largest collectors, largest irrigation canals, and so on. I think there are some representatives from Hyderabad service. They can explain this much better. So I would say, of course, we have still to improve our monitoring from agricultural fields. To say collected drainage waters. For example, I don't know that somebody surveys the uranium pollution of collected drainage waters. I think we don't conduct determination of uranium pollution, our agricultural runoff. Thank you. Sorry.
I don't think that was from us. Amy, did that answer your question?
Yes, thank you very much. That was extremely helpful.
Do we have other questions from the audience? Remember, we're here to learn. You are not being evaluated for your academic or scientific skill. This is our opportunity to share. If you have a question, you can type it in Russian or Uzbek or English in the chat box if you're afraid to speak. That's okay too. Amy, you said you had other questions. Would you like to go ahead with those for the moment?
Sure. Well, we're waiting for others to maybe ask a question. Another question I have is, as climate change worsens and water scarcity increases in countries like the United States and Uzbekistan, are water conservation practices being used in Uzbekistan? And if so, what types of conservation practices? One of the things I showed was rainwater harvesting in my slides. That's one type. I was just curious if those types of practices are being looked at in Uzbekistan or used in Uzbekistan, just out of curiosity. Thank you.
So thank you. I mean, if nobody wants to reply, I would like to inform you about our experience with using rainwater. Yeah? You know that we have blue water, green water, and gray water. So last year we have tried to prepare special project proposal regarding the use of gray water and rainwater in Uzbekistan. But we had very big problem because drinking water costs in Uzbekistan very cheap, and collecting of rainwater and gray water and treatments, further treatment costs much money. It's very expensive. So it can be profitable in maybe in the US, maybe in Europe or in the developed countries, but in countries in transition like Uzbekistan and in other countries, developing countries where drinking water costs very cheap, it's not feasible, I would say. This is the main problem. Otherwise, we can collect rainwater, of course, and use them, also gray water. Thank you.
Thank you. That was really very helpful and insightful. I really appreciate your sharing.
Does anyone have a question for Neil or Amy about some of the case studies that they presented? I think Amy focused on the whole history of the clean water law in the United States. That's her focus being more on also the political history and the policy behind it. And Neil spent quite a bit of time talking about groundwater. But if you don't have specific questions about that, but you have more general questions, we can also support those. I want to also remind everybody on the call to please provide us in the chat box if they can, who they are, where they're from, which organization, because that's helpful for us to understand.
Yeah, sorry, may I have a question? So, Dr. Nile, as I said, we don't conduct large-scale monitoring of uranium pollution of groundwater sources. What do you think? What is the implications for Uzbekistan not conducting monitoring of uranium pollution of groundwaters? This is the first question. And second, what you suggest to us for Central Asian countries, what to do based on US experience? Maybe we have to organize large-scale monitoring of uranium and arsenic pollution of groundwaters. Or what do you think? What is the future actions needed from our side?
I'm only taking easy questions tonight. That's very complicated. I don't feel qualified at this point, but I will make some statements with that disclaimer. You're basically a closed basin, so you have to have problems eventually with salinization. The simplest of all, but very difficult to treat. So I think one of the simplest questions then would be, as a place to start, is how, I assume, this is a big assumption, I assume your groundwater resource will get slowly saltier, more saline. So what would be useful would be to have data on the age of the groundwater that's being used currently. Look at the age distribution with depth, and physical models, well, numerical models of the rate of groundwater flow. I'm sure there are many other things, but you can treat for nitrate, you can treat for arsenic, but salinity is very difficult to deal with. It's a problem in arid areas in the United States. Generally speaking, it's changing very slowly, but hopefully we'll be around a long time. So I would say that that's simple to measure, the salinity, but we found in trying to answer questions about contamination, the use of isotopes and other tracers of age and source were tremendously useful. So in terms of suggestion of things that can be done in the future, I mentioned consistency. I have a great presentation that the person that was studying river water quality in the country. And they contacted every water agency in the country and got their data. They had 25 million analyses for phosphorus. But because each of the laboratories did things a little differently, they had to throw away, they could not use 95% of the data. So I think there's probably locally and regionally activities that are looking at water quality, but capturing that data digitally and sharing it in the clearing in one location. And in doing so, describing the method of collection and the method of laboratory analyses, then that one sample can be used for many different purposes. The EPA started that process decades ago on one national database and asking different agencies, local and regional, to provide their data to that database. But it took a very, very long time to make it standard. And so it's a lot of work. It's asking people locally to do things different than they used to. Even here, many people just have paper records from the laboratory. So if there's a carrot, if you could do some technical assistance to local agencies so they can make their data digitally available, in the long run, it will be amazingly valuable. Simple step.
Thank you very
I hope
much.
that was helpful.
Are there any other questions from folks in the audience?
I have a question for the audience. Oh, sorry, did somebody just speak?
It was
I
me.
was going
You're
to
good.
ask if the people in the audience after this presentation today have some thoughts on areas that they find interesting that they would like to learn more about with respect to U.S. water quality and expertise. Could they share that with us or put that in the chat box? I will also leave my email in case they want to send it to me afterwards, but we would appreciate your ideas.
And just to add on to that, again, we will be sharing the presentations from today. So I understand there was a lot of technical material and information in those presentations. And for people who want to look at it a little bit closer, we would encourage you to view those presentations in Russian, Uzbek, or English per your preference, and follow up with the embassy to ask questions or make recommendations about topics that would be useful and of interest to you in Uzbekistan. We would very much appreciate this.
Let's put the Google link one more time because some people have arrived a little bit later. And we will we'll stay open for about 10 more minutes. The presentations are done. We're gonna stay open for 10 more minutes in case you have some questions that you think about a little bit later, but otherwise we will, encourage you. You can leave if you like, or you can stay longer if you have questions you want to raise. But please do download the presentations so that you have a chance to review them. And can we also add them in English to the drive so that people who prefer English can read them too?
They are there in English.
Okay, thank you.
No problem.
So as I said, we'll stay open about 10 more minutes in case people have questions. It really depends on the individuals, but otherwise we will, we have another session coming up in about 2 weeks. And we will, if you don't have the information, please let me know. If you prefer something to be sent to you, put your email in the chat box. We can also reach out to you by email.
Thank you very much for organizing this online seminars. On behalf of TMA, I would like to say we are grateful for having such a great it's very helpful for us and we can
Any final questions from the group? Otherwise, as Beth indicated, we hope to do another session in a few weeks. We expect that we may have questions or be seeking additional information about what would be most useful. And we hope that you will work with us as partners to tailor these presentations to the highest priorities for Uzbekistan in terms of water quality. And please feel free to send me your email addresses and send your email addresses to the embassy. We will make sure that you get the slides from today's presentations. Wonderful. I see in the chat that there have been folks able to download the presentations and that they will share them. That would be amazing. Thank you so much. For folks outside of TMA, I know we have representatives from other agencies also on the line. Please feel free to share your email addresses or use the link we've sent in the chat to access the presentations. Thank you. If there's nothing further, I think we can go ahead and stop the recording. And we will leave the room open for a few more minutes for folks to send us email addresses and wrap up any conversations they might be having over direct message. Otherwise, we wish you all a wonderful rest of your day and rest of your week, and look forward to hopefully seeing you again soon in a few weeks for our next presentation. Beth, is there anything else from the embassy that you would like to add? Or Amy and Neil, would you like to say anything before we close up?
I look forward to learning more about water quality in Uzbekistan.
Yeah, thank you so much for your time this morning. Really appreciate it. And as Neil said, we really look forward to learning more about water quality and any help or assistance we could provide in that area. Thank you again.
I just want to thank all our participants who were here today. I also want to thank our interpreters for their support, and again, thank the U.S. government agencies, the Department of Interior, which sponsored this program, the Environmental Protection Agency, and the U.S. Geological Survey, which provided our experts, and of course the Department of State, which is providing you with this platform today. It's a group effort, and it's nice that we're able to share this information with you, and we look forward to seeing you again soon. Thank you to everyone who's putting on emails.
Yes, I know Beth and I are frantically scrambling to write down all the email addresses to make sure we don't miss any. So we will certainly be following up with you. Otherwise, thank you so much, everyone. I will stop the